There you go. Thank you, Steve. Well, anyway, it's really a pleasure to be here. This is like a homecoming for me. As I mentioned, I am a former, as Steve mentioned, I'm a former student from here 40 years ago. I defended my thesis 42 years ago this month on Friday, the 13th, November 1981. And but now my son lives in Louisville, so I come out here quite frequently to visit him. And I actually even bought a house in Louisville that we are maybe going to at least spend part of the year at after I retire next year. Formally, August of 2024, I'll be formally retired. But I plan to stay very active in research with Steve and other people that I former postdocs. One of the nice things about having students is you get to have lifelong collaborators and friends, and Steve is one of those. So what I'm going to talk about today is some work I've done in the last couple of years on massive star magnetospheres and how material builds up in these magnetospheres and breaks open and induces reconnection. And what are the consequences of that? What are the diagnostics of that? And what are the future implications of what we want to study? So to set the stage, the word magnetosphere really got invented in the 1950s when people realized that the Earth's magnetic field trapped plasma from the solar wind. It was even before the solar wind was really known that there was this belt of plasma trapped by the magnetic field of the Earth. And of course, that got named the Van Allen belts, at least by Americans, because the instruments that first detected them were on satellites that were instruments were built by the group at Iowa at Van Allen. But the key idea now is we realize that there's this real strong connection between solar activity and the Earth's magnetosphere, and indeed all the magnetospheres of the planets, and that the plasma, most of the plasma in the Earth's magnetosphere originates from the sun getting trapped. So the idea is that you can actually think of maybe the sun itself, the solar corona, as being a magnetosphere. The difference being is that the magnetic field of the sun, the plasma that fills the magnetosphere is coming from the sun itself, as opposed from an external source like solar wind for planetary magnetospheres. But here you can see a beautiful white light eclipse picture of the sun, and these striations are all due to magnetic structure on the sun. And the solar corona, of course, is very hot, wants to expand out in a solar wind, and that solar wind drags the magnetic field open into these radially configurations. These are sometimes called helmet streamers because they resemble a World War I German army helmet. So a key paper in this field was by Terry Newman and Roger Kopp. They were both at HAO when I was a graduate student. And basically they did is they took a dipole magnetic field and then just allowed the solar coronal expansion to try to expand. So the dipole, the original dipole, was this dotted line, and then here's the actual dynamical self-consistent solution. They didn't have fancy MHD codes in those days. They had to do it with an iterative solution, but you can actually run as a test problem on your modern MHD code. You can put a magnetic field in the solar corona and it turns into the Newman-Kopp solution. It's quite a beautiful result. So the idea is that the field now has opposite polarity from different hemispheres here, and then in between there's a current sheet. And the current sheet helps generate more magnetic field. Now I study very massive stars, stars that are typically anywhere from a few times to 100 times the mass of our sun. And they have very strong radiation fields. They're very bright. The luminosity of a star tends to go as the cube of its mass. And so the consequence of that is that when you get to very high mass stars, the radiation field is so strong that they drive away powerful stellar winds through the scattering of photons off of spectral lines. And these winds can be 1 billion times more dense than the solar wind. Mass loss rates of 10 to the -5 solar masses per year compared to the sun, 10 to the -14. Now, classically, people thought these winds should be more or less just beautifully spherically symmetric because the envelopes of massive stars are purely radiated because hydrogen doesn't recombine the way it does in the sun. So you don't have the convection zone, which drives the rotation convection dynamo that causes all the activity of the sun. You're supposed to have a more or less convective core due to the sensitivity of nuclear burning, but you don't you have a radiative envelope. So there's no way to really generate a magnetic field in the present day star, but in its history, it may have gone through stages which generated magnetic field and then left behind a fossil field. So the fields that we detect in these massive stars are probably generated a long time ago in are fossils. They're not being actively generated by a dynamo. And so there's a project that was first founded by Greg Wade called Magnetism in Massive Stars, which I participated in. And basically, these stars show magnetic fields that are of the order of anywhere from 100 to 10 kilogauss in the pretty large scale fields. And so if we take on the HR diagram, they sit at the upper top of the main sequence. They're mostly main sequence stars, and these are just the sample of magnetic stars that are along the high end of the main sequence. This was published in 2013 by Vero Petit, who is a collaborator and was a former postdoc of mine. She's now a faculty member. And at the time, there were about 64 known magnetic hot stars, hot being earlier than, say, middle B, hotter than B5. And anyway, the key point here is that these fields, these are all different kinds of stars along the main sequence, and but they're primarily, they're very strongly magnetic, and they have magnetic fields that are very large scale, mostly, and and so what happens now when you take a star that wants to have a very powerful mass loss, and you add magnetic field to it? And so, so the key question is this battle between the kinetic energy of the wind and the magnetic field energy, which is trying to confine it. So if you can define a parameter, it's kind of like the plasma beta parameter, except that I always thought that plasma beta should have B in the numerator, which doesn't. So I made up a parameter eta, which is not the ratio between the magnetic energy and the pressure, but rather the magnetic energy density and the kinetic energy density of the outflow. And if you just do some arithmetic, you can basically turn this into a parameter where you solve for a radius where this parameter will go through one, because after all, the magnetic field, if it's a dipole, is falling off like 1 over r cubed. And if then you square it, that's 1 over r to the minus 6. So, so the key idea here is that at some point the wind will win out, because once the wind reaches terminal speed, the density just falls off with 1 over r squared. So
here by V, this is a bulk flow, not a thermal velocity.
This is the bulk flow, not the thermal. If you were to put the sound speed squared here, this would be the inverse of the plasma beta. But these winds are very highly supersonic. The winds from these stars are very cool by comparison to the solar corona. They're typically 20, 30. They're of the order of the temperature of the star, the surface temperature of the star. They don't have hot coronae the way the sun does.
But are they fully ionized?
Yes. Yes, they're 30,000. Typically to affect the temperature. The fully ionized are hydrogen. They're obviously minor ions that are still retaining electrons. Okay, anyway, you can define a parameter, which you can convert this parameter, say the surface value of the field at the star, surface radius of the star, the mass loss rate of the wind, and that becomes a parameter which sets the scale at which the Alfven radius will since this is falling off like 1 over r to the 6th, the density is like 1 over r squared, there's a 1 over r to the 4th fall off. And so if you solve for that, the 4th root of this parameter will set a radius at which the magnetic field can no longer be closed, but will be ripped open. And so we call that the Alfven radius after Hannes Alfven. Now, so what happens is if there's no rotation, material that's trapped, because these winds become supersonic very quickly, they're not like the solar corona where they don't become supersonic until Parker radius. They become supersonic very quickly, and then they shock, the two streams come together, they shock, the gas cools, and it falls back down on a dynamical time scale. And so you can see you get this very kind of chaotic kind of phenomenology for these stars if there's no rotation. But if you add rotation to the mix, then now you have a new parameter, which is the rotation speed to the orbital speed or critical speed for gravity. And then if you want to solve for where, if it's rigid body rotation, the material in rigid body rotation would be in Keplerian orbit, then that would be equal to this parameter to the minus 2/3 power if you just do the arithmetic. And so that Kepler co-rotation radius then, if it's a rapidly rotating star, in this case where this rotation parameter is like a half, then now you're really close to the star and the Alfvén radius is further out. So what happens in this region between the Kepler radius and the Alfvén radius? Material can't fall back down because it's beyond the Kepler radius, the net force is outward, centrifugal force is outward. Material would fly outward, except the magnetic tension is holding it down. And so material just piles up in this region, and you get an accumulation of plasma. And so we call this a centrifugal magnetosphere. The other kind of case would be like a dynamical magnetosphere because material goes up. It's kind of like a juggler. It just throws things up in the air, it goes back down.
So at the Alfvén radius, is the Kepler velocity at the Alfvén radius less than the Alfvén velocity?
Typically, that's a good question. I have to think it through. But the point is that up beyond here, the rigid body rotation is a pretty good approximation. And then at the Kepler, at the Alfvén radius, it basically material, the wind takes over and strips open the field. But in between the Alfvén radius and the Kepler radius, material is sort of forced to co-rotate, and magnetic tension keeps it in place against the centrifugal force that's greater than gravity. So those are the two things. If you have this parameter eta star, which depends on the field strength, the mass loss rate, the wind speed, and this other parameter, which is the rotation over the orbital speed, then those two parameters determine the Alfvén radius and Kepler radius. And so we can sort of define two different domains, one in which the Kepler radius is far away because it's a slow rotator. That means that then the material that's trapped in the closed loops just falls back down on a dynamical time scale. So we call those a dynamical magnetosphere. And then if there's a case where the Kepler radius moves inward from the Alfvén radius into this region which there's material trapped. So those are the two different domains that determine. So now let's ask ourselves, if we just do a study of this with an MHD code where we drive the wind and we have MHD to hold material down, what happens in those simulations I showed you. But when you look at a movie, you see this beautiful dynamics, but it's hard to see the overall global evolution. So what we came up with was this way to characterize the mass distribution by just counting up the total amount of mass in a radial segment as adding all the mass that's confined in this dense material, and then plot that as a function of radius and time. So there's the Kepler radius. Everything below the Kepler radius is falling back down on a dynamical time scale. Everything above it builds up. That's why you have dense plasma right here. And then every once in a while, there's these breakout events, okay? And so now what we can do is a parameter study, and we increase the rotation rate or increase the magnetic field strength, and we look at the different phenomenology we would get in this mass distribution. And you find that if there's weak field and weak wind, a weak rotation, no rotation and weak wind, then you just get these little streams. But then as you go to higher, stronger and stronger magnetic confinement, the Alfvén radius goes up, you get more material trapped that falls back down if there's no rotation. But if you add rotation in it, the material just builds up to this dense magnetosphere. So that's the key idea, is that these are dynamical magnetospheres and these are centrifugally supported magnetospheres.
So can you just remind me how the Alfvén and how RA and RK vary horizontally and vertically here?
Well, these are just increasing. There's the magnetic confinement parameter, and the Alfvén radius is the fourth root of that times the stellar radius.
The Alfvén radius is the solid line.
Is the solid line, and the dotted line is the Kepler.
Okay.
Okay. Mm-hmm. So you can see that here, the Kepler radius is above the the Alfvén radius is above the Kepler radius, and that whole region between the two material is tending to pile up. Okay, so now what we can do is take the observations. We can infer the magnetic field strength from spectral polarimetry. We can feel the rotation from just the fact that, there's a modulation with rotation. And then we can plot things on a plane that has rotation on the vertical axis and magnetic confinement on the horizontal axis. And I've done it so that fast rotation is on the top and slow rotation on the bottom. That means the Kepler radius is getting bigger and bigger as you go down here, right? And so now there's this line where the Kepler radius is equal to the Alfven radius. Everything above this line has a centrifugal magnetosphere. Everything below this line has a dynamical magnetosphere. So that's the way to classify. That's kind of like almost like an HR diagram for magnetospheres, right? It's a way to classify the two different kinds of magnetospheres. Now, here's what's interesting. If you actually look at the labels here of what the types are, I'm going to highlight now the O stars. The O stars are more luminous. They're more luminous. They have higher mass loss rates. What does that mean? They have higher mass loss rate in a powerful magnetic field. Then they're going to spin down because magnetic field acting on the wind is going to act like a torque, just the way it does spin down of the sun. And so all these stars, all these O stars have been spun down because they're very powerful winds. Combination of powerful winds and strong magnetic field means that they spin down. And so some of these stars have rotation periods of 50 years. This one down here, for example. And almost all of the O stars are below this, they all have dynamical magnets. The only exception is this guy up here, but that's in a binary system and it had mass exchange. So it's called Plaskett star. Anyway, so now we can go through and discuss what happens for these two different domains. That's normally what I would do in a talk. I would talk about the dynamical magnetospheres, and then I talk about streamline. But I want to focus on the centrifugal breakout phenomena. So I'm going to just go through this really quickly. The first thing that I do want to do, however, is talk about how the stars spin down. This is basically an extension of the Weber and Davis theory that was developed for the solar wind. That the angular momentum loss is related to the mass loss rate, omega, the rotation frequency, times Alfven radius squared. That's a formula that comes directly out of Weber and Davis. The only thing is that Weber and Davis assumed that the field can be described as a split monopole. But in reality, we have dipole magnetic fields. And so if it turns out, if you want to generalize that Weber and Davis formula, you have to take into account the different variation with radius or the magnetic field strength. And when you do all the arithmetic, the Alfven radius squared, go through all the algebra, I won't go through the details. You find that the spin down time is related to the mass loss time, that's mass over mass loss rate, times this parameter, which just connects the moment of inertia with mr squared, okay? And the magnetic confinement parameter to 1 over n power, where n is the order of the pole of the magnetic field. So for dipole, n is equal to 2, for monopole, n is equal to 1. And so since most of our stars are dipoles, we have this formula for how the stars spin down. And if you plug numbers in for O stars, that spin down time is less than 1 million years. And even O stars live for tens of millions of years. So these stars will all spin down on their main sequence. So the next thing is putting these on the diagram. You find out that all the stars on this blue area must be older than their spin down age, how long it would take them to spin down. So these stars are all been spun down, but these stars are not. All the O stars have been spun down, but there are a lot of these stars out here, and they're mostly B stars. They didn't spin down yet because they have a lower mass loss rate, therefore they have less spin down. And so these stars are the ones that can be centrifugal magnetosphere cases. They're the ones we want to look at for centrifugal. Now, like I said, there's a lot of work I've done on the dynamical magnetosphere. Here's a simulation of a 3D simulation of a dynamical magnetosphere. Then we've derived things like the dynamic spectrum from these stars. I'm not going to go X-rays from them. I'm just going to go through these really quickly because I want to focus. We can come back to that later. I want to focus on the centrifugal magnetospheres. Okay, so I just zoomed through that. I know that was like nobody can follow what I did there, but I just want to say we've done a lot of work on those kind of stars. It's just that I want to focus on centrifugal magnetospheres for the rest of the talk. So the key thing here is that we have the rigid field confines plasma, and now that plasma builds up to higher and higher density, and what actually ends up emptying it? You're continually feeding this magnetosphere with the stellar wind. So what's the question we want to ask ourselves? So the first thing to try to do is to figure out what is the form of the confined plasma takes when they have a combination of rotation and magnetic tension. This is a model in which we basically just assume that the magnetic field is like a rigid pipe, and we just do one-dimensional hydrodynamic simulations and stitch them all together. And this is what happens. Whoops, sorry about that. You basically find that material gets confined at the magnet for aligned rotation. That is the magnetic axis, the rotation axis. There's the dynamical magnetosphere, and then this material is just trapped. So of course, if it's aligned rotation, material is just trapped at the common rotational magnetic equator. But what happens if the magnetic field and the gas are not aligned? Well, it turns out you can solve that problem as a centrifugal potential balancing against gravity, and you can solve for the minimum potential surfaces. And they have forms that look like warped sheets and so forth. And these are the places where a combination of rotation and magnetic guiding will tend to make material accumulate. And so then you can take those models and you can say, well, let's now put up a model of how the mass is distributed along these accumulation surfaces. And that can be completely analytic. It's called the rigidly rotating magnetosphere model. And this is work that was done by Rich Townsend, one of my former postdocs. And basically you can see you make these beautiful images of what a rotating magnetosphere looks like, but it's all analytic. It's quite remarkable. And not only that, you can then synthesize observational diagnostics from this model. Here, for example, is diagnostic for the Balmer emission, because material piles up, it's very dense. It likes to give off photons by H alpha, just like an H2 region does. Here's when the cloud goes in front of the star, it's going to make a little eclipse. It's almost like a little planet going in front of the star. And then here's the spectral calorimetry of what the longitudinal magnetic field would be. So the point is that this model can be very well tested by comparison to observations. So let's take, for example, the prediction of the spectrum that would happen in H alpha. Notice that H alpha spectrum is varying in a very characteristic way. What if we now take that variation and just give it an intensity as a function of rotational phase, Doppler shifted from the line center by the rotation velocity? You get this really kind of nice double S wave structure. Well, that's what you predict by this rigidly rotating magnetosphere analytic model. This is what you observe for H alpha. And that's quite remarkable that a simple model like this can model the dynamic spectrum of use that you see. The agreement is not perfect, but it's extremely promising. And then the other thing is that you can then follow the photometric light curve of these stars and find out when they're going through eclipse. And then you can follow that for many, many years. And what you find is that then if you put this on an observed minus computed diagram, that the star is actually spinning down slowly because it's losing angular momentum. You can actually directly measure the spin down of the star by following the little magnetic eclipses over many, many years. So this was from 1976, the original observations. These are data that was done by my student, Mary Oksala, and Rich Townsend. Anyway, that's a really beautiful result. Okay, so now this is where I'm finally able to get to the part of this talk, which is, okay, we have this phenomenology where the wind feeds this centrifugal magnetosphere. How does the mass finally empty? Okay, and this is a slide taken from a paper that Steve and I wrote in 2018 when I was here on sabbatical 7 years ago. We did some work, and there's basically 3 different ideas. For dynamical magnetospheres, it's pretty obvious. The material goes up and it comes back down, and it's like a juggler putting things up in the air. It falls back on a dynamical timescale. But for a centrifugal magnetosphere, there's 2 possibilities. One is that the material just piles up to the point where it becomes so dense that centrifugal force, magnetic tension cannot balance against centrifugal force. The other possibility is that the fields are not ideal MHD. They're turbulent, and that there's cross field transport. And so that we call the leakage model. So which one of these is proper? And so this is kind of a cartoon version of the 2 different scenarios. Breakout is when the magnetosphere is defined by the strength of the magnetic field. It's like the volume of a glass. If you fill it up beyond that, it's going to it's going to spill, which is this breakout effect. Leakage is when there's actually that the glass is not a good container, and some of the material is leaking out. We want to ask ourselves which one of these. So here's the paper that Steve and I wrote about how non-ideal MHD processes can allow transport across the field and the magnetospheres leak. And so there's two processes that go on there, sort of a diffusion process, which go in either direction, or a drift process, because after all, the centrifugal force is trying to push things outward. And so if material can just, go across the field line temporarily, it'll always want to have a bias of going outward. And so we have a paper that works this out, and Steve put in some very nice estimates of the turbulence that might cause the transport to be non-ideal. And these curves here are different predictions for the density distribution for different kinds of models. But the other possibility is that the material just builds up to the point where it just breaks open the magnetic field. And we saw that in the simulations earlier. So it turns out in this appendix, which originally developed this model for the rigidly rotating magnetosphere, in an appendix to that paper, we discussed what would be the density that would be necessary to overcome this magnetic tension. So the basic force balance, here's magnetic tension. It goes like the magnetic field strength b squared over 4 pi divided by a characteristic length scale for the disk, for the accumulation material. And then here's this mass density times, that's the rotation frequency, that's the centrifugal force, and then there's gravity. So that's the key balance. And now if you go to this and say, well, let's just multiply HM times B, that gives you a surface density. Volume density times the length gives you a surface density. So there's surface density times centrifugal force minus gravity is equal to B squared over 4 pi. So now let's go a little bit further away from above the Kepler radius, the centrifugal force is going to be overwhelming gravity. So now we can actually come up with a relatively simple formula. The surface density that will be balancing the magnetic tension depends on B squared over 4 by G centrifugal, but G centrifugal is just omega R squared. So now you have a formula for what the surface density should vary like with radius. And it goes like R to the minus 7, okay, because of the B squared going like R to the minus 6, and then there's an extra R in the denominator. So how does this compare with what we get from simulations? Well, here are 2D MHD simulations for 3 different values of this magnetic confinement parameter. And you can see there around the Kepler radius, there's this fall, there's a peak, and then there's this fall off. And if you then take into account the scaling of this sigma star with eta star, and we just put them on the same scale, whoops, then they all kind of follow a nice kind of scaling relation that, and it turns out to be R to the minus 6 instead of R minus 7 because of the details of the numerics, but that's pretty good. And so now we have a way of actually predicting when a disk will become optically thick in H alpha. The optical depth in a line like a recombination line depends on the density squared because it involves an electron recombining with a proton. So you have to have tau H alpha goes like density squared, but that goes like this value here, R to the minus 12, right? So what it tells you is that as you make the value of this parameter 1, and then increase it, you start getting more and more emission, and then you start forming an emission line in H alpha, right? Because you're integrating this surface brightness over the material. So the key lesson here is that in order to get the emission, you need to make the disk optically thick in H alpha, and so you need to make a parameter where what value of the magnetic field makes tau H alpha equal to 1. Well, so if you do that and you plot as a function of luminosity, now remember these stars are driven by radiation. So a higher luminosity star has a much more mass loss rate. And here's a plot of the observed value of the magnetic field scaled to the Kepler radius. So log of the B value of the magnetic field at this Kepler radius, divided by the value of the Kepler radius that theory predicts will make the disk optically thick. Tau equal to 1. And what do you find? All the stars that are H alpha emission, at least the ones to the right of this line, all the ones that are H alpha emission are above that line. So what it tells you is that the density of the disk, as inferred by H alpha, is exactly the density that's needed it's the critical density for breakout. So this is telling you with a smoking gun that at least for these stars, the mechanism for emptying the magnetosphere is breakout, not drift and diffusion. Okay, so there we go. For every star above log L greater than 2.7 times the sun, 10 to the 2.7 L sun, breakout is the mechanism by emptying the magnetosphere, not leakage.
Hey, Stan?
Yep.
What is it that theory actually sort of predicts for the time dependence, right? Is it just that it builds up to that critical density and then some material leaves and then it's a little
bit like this picture.
Okay.
Right?
It's just hovering around that.
It's hovering right around here. I mean, this glass is always 99 to 100% full, right? It's always, you put a little more water in it, it has to spill open. And the amount of water in the disk is the amount of water in this glass, is the size of the container. It does not depend on the rate at which you put the water in. Right? Where if it was a leakage model, the amount of water that would be in the glass would be a competition between how fast you're pouring it in and how fast it's leaking out. Okay, so for this part of the HI diagram, centrifugal breakout is clearly the explanation. But what about these guys? They're above this value, and yet they don't. Why? Because their luminosity is so low that their mass feeding rate is very low. And if there's a little bit of leakage, maybe it's a little bit of leakage, but it doesn't care. That glass, the mass is being fed so fast that leakage doesn't count, doesn't make any difference. But here, maybe it does. So this is an area that Steve and I want to take our theory and apply it to. We haven't done that yet. That's one of the reasons why I came to visit. But we want to actually see if leakage. Now, there's another possibility. These stellar winds are driven by photons hitting spectral lines, carbon, nitrogen, oxygen, iron, nickel. And then that momentum has to be shared with the protons to drag them out because they don't get any momentum directly. That requires a collisional coupling. And if the density is too low, then the protons will become separated from the ions. And so this could just be that you don't get any protons driven in the wind. Therefore, you don't make H alpha, but you just have a metal wind. So there's two possibilities for explaining this lack of hydrogen emission. One is that the gas is got leakage, or that magnetic field has leakage. The other possibility is that the wind becomes a metal wind. Any questions? So that's the key. That's the key smoking gun. We just saw the smoking gun that these stars are converted. That is to say, for the luminous ones, earlier than say B5, they're all centrifugal magnetospheres are controlled by breakout. Now, what is the other thing that happens if there's centrifugal breakout? There's reconnection. And it turns out that almost all the stars that are H alpha emitters are also observed to be non-thermal, circularly polarized radio emitters. Those stars have non-thermal electrons that are gyrating around the field and giving off photons by gyro emission, giving off radio emission. But what's remarkable is that this is unfortunately not in the backward direction. Luminosity is higher over here, but you can see that the ratio of the Alfven radius to Kepler radius is a measure of how important rotation is, as well as magnetic field. They all require a combination of rapid rotation and strong field. And so so here you can see.
Can I ask,
Sure, go.
Do we know, is this radio emission steady or is it bursty?
Well, the
You know?
observations are, with these big telescopes, and the number of Janskys is pretty low, so the time resolution is a bit limited. But people are looking at them more and more to see for variability. But you see, one of the things I would like to emphasize is in this model, this is a 2D model, the centrifugal breakout is a huge event. It empties the whole magnetosphere. But in 3D, this breakout can occur over here, and then over there, and over there. In other words, it can occur as a series of very small breakouts. So you don't necessarily predict strong variability, okay, from such a model, if you take into account the 3D nature of it. Anyway, okay, so now let's ask ourselves, what kind of energy is available if you break out of this magnetosphere? So this is one of the reasons why I went through the Weber and Davis discussion earlier, because ultimately the idea here is that, so this is a paper I wrote a couple of years ago, I guess last year, on powering electron acceleration by centrifugal breakout. And the key idea is to take the energy source is the rotation of the star, but then that rotation gets if you have the rotation change, the rotation rate changing, there's an associated luminosity, right? If you slow the star down, there's energy available. And so now you use the Weber and Davis scaling laws to convert that rotational energy loss into a formula. And then if you make some assumptions about the ratio of the Alfven radius to Kepler radius, in this case, I'm going to assume a monopole. You get a scaling law that includes magnetic field strength squared, the volume of the star, radius cubed, rotation frequency squared, and then you see rotation times volume times magnetic density. That's an energy per unit time, right? And so this would imply that the magnetic field is being dissipated on a time scale close to the rotation period. But of course, that's just the conduit of the energy from the rotation of the star. The magnetic field is just a conduit for the energy to be lost. All right, so I went through this pretty quickly. If you didn't understand this completely, I can accept. We can go back over it. But here's the key slide. The original idea was that these radio emission came from the magnetic reconnection or from acceleration of particles in the current sheet. But you see, that doesn't require there to be a rotation. That's just the stellar wind expanding the magnetic field. And so the original paper, the original explanation by Trilio, 2004, was that the particles that we see in these radio emission electrons were accelerated in the current sheet. But then rotation wouldn't have any role in the observed radio emission. So we think it's centrifugal breakout. And the centrifugal breakout scaling goes like this. And then here is the observed radio with the predicted centrifugal breakout energy. Here's if they were equal to each other. But of course, when you have energy reconnection, only a small fraction of that energy is going to go into accelerating the particles that end up emitting radio. So there's a huge efficiency factor. In this case, it's about 10 to the minus 8. But the fact that the slope is almost exactly is right. The correlation coefficient is 0.87 here. It tells you that this is a very likely mechanism, or at least it's a potential mechanism for explaining the radio emission. That centrifugal breakout is the source. So that's the punchline of this talk, really. Now here's the other thing that's really cool. There's all the early type stars. There's the scaling relation that they observe. But now if you extend this down lower and lower, there's another population of magnetic stars called ultra-cool dwarfs. These are things that are right on the border between M-type and brown dwarfs. And they are observed to have powerful magnetic fields and be rapid rotators. But that's a completely different mechanism for their magnetospheres. They're not driven by radiation. They're more like probably a coronal type of mass loss or something, and yet they fall on the same ultra-cool dwarf. They follow in the same scaling relation, just down several orders of magnitude. So it's a suggestion that there's some kind of universal explanation for these kinds of two different kinds of stars for their radio emission. But what really is remarkable is if you extend this down many, many, many orders of magnitude, it also explains the radio emission from Jupiter. So, so that is a strong suggestion that maybe at heart here is the detailed model that we developed for the stellar magnetospheres might be much more broadly applicable. And so that's kind of where I've been pursuing some inquiry. So I invited this woman, her name is Melody Kao, Kao. She's at University of California, Santa Cruz, and she recently had a paper published in Nature that used VLBI to resolve one of these ultra-cool dwarf radio emitters. Now, you see, these ultra-cool dwarfs are very low luminosity, and if you're seeing them, they're going to be really close. All the O stars, all the O and B stars, the B stars that we've been talking about, they're hundreds of parsecs away. It's very, very hard to use any kind of resolution to be able to resolve their magnetospheres. But these guys are close by things. So you can use VLBI to resolve them. And when they did, they got these kinds of results for the radio emission, 2 different lobes. And then if you went a little bit carefully, they found also evidence of both magnetosphere emission from the radio as well as aurorae. Aurorae occur when the electrons impact the stellar atmosphere, the stellar atmosphere. And then they produce emission of all kinds, including radio. And but what they found in this case is that you find 2 different components of the magnetosphere.
How do they distinguish these components?
Well, the idea is that aurorae would be close to the star and the other stuff would be far away, right? You can read the paper and see if that's any more detail than that, but I think that's the basic argument. There are some spectroscopic differences between the 2. I mean, I'll have to go back and anyway, all I'm trying to say, and then this is the beam. So the fact that this is elongated is just due to the radio beaming of the VLBI. All right, so I have a former postdoc at Delaware who's now in Australia at the CSIRO in Australia, the Radio Observatory in Australia. And her name is Bernalee Das. And she and I have now been trying to model the radio emission from these magnetospheres, where we just take a dipole magnetic field and then we introduce a population of high energy electrons staying from reconnection. We don't do the full Monty at this point, but I'm very interested in, people who can model reconnection and acceleration, and I understand Greg is an expert on that. But anyway, what we're doing is just a simple model of saying, okay, let's introduce a population of high energy electrons, and then just let them gyrate back and forth. They mirror back and forth because they conserve magnetic moment, or they almost conserve magnetic moment. And then they emit, as they do, they gyrate, they follow this formula for the energy time scale that they lose energy compared to, basically it scales with the magnetic field. And so when you get closer to the star, the magnetic field is much stronger, they get a lot more emission. So the tendency is to have the emission be down on the foot points. You introduce, this is introducing electrons very closely along the apex of the loop. This is introducing it more broadly. This is introducing it, and you can see that even the case where they're apex, you still have a lot of emission down the. So now the referee on this paper was a guy named Paolo Lito, who studies observes these radio emissions, and he criticizes us for not including collisional cooling, because it says if you have like these high energy electrons, not only do they cool by gyro emission, they can cool by impacting thermal electrons. And so what we did is in the next paper, which is still in prep, we've included this cooling effect by saying every time by accounting for the amount of cooling that will happen whenever you cross the centrifugal magnetosphere. There's a lot of density there. There'll be a lot of electrons. And so this is the same case. This is the same case as before without this cooling. And now we add
the color scheme is emission?
Yeah, is emission strain. And so you add, this is the amount of energy you add, this is how it gets distributed in latitude for the 3 different cases. And And here you can see that this is we ignore cooling, then here we add cooling, and of course, there's much less emission. And this is already relative to gamma of 11. So if you go to gamma of 1, it's essentially get nothing. And here's if you do gamma of 100, it looks pretty good because collisional cooling is inversely proportional to the energy squared, the cooling time scale, right? So the higher the energy, the less you have to worry about it. But what it tells you is if you're seeing radio emission from these stars, that the electrons have to be they have to be relativistic. They can't just be, mildly relativistic, gamma of 40, 1.1 or something. They have to be relativistic. And so that is an important conclusion that, we have to figure out some way to have this centrifugal breakout reconnection accelerate particles to gamma electrons to gamma of 10 plus or close to 100. And that's a challenge for modeling reconnection. All right, so now the final few minutes, I want to just connect on to the broader area of magnetospheres. So Jupiter has a magnetosphere, just like the Earth. Its magnetosphere is ginormous because the magnetic field from Jupiter is very strong by comparison to the Earth. But it has, not only is it stressed externally by the solar wind pushing on it, it has this satellite, Io, which is emitting sulfur ions through its volcano. And associated with a lot of the radio emission is tied to the orbital phase of Io. And so the question is, as the Io shoots these sulfur ions out of it, they get ionized by the solar UV light, and then they get trapped on the magnetic field. And at that point, you're feeding plasma into the magnetosphere from internally, sort of like what you do with a stellar wind. Instead of just being stressed from outside, you're now stressing it from the inside. And the question becomes, what happens to this plasma, this Io plasma torus? And how is it transported outward? Does it build up to the point where it forces the magnetic field to break open, or is there some transport that's related to the non-ideal nature of the field? So this is an area that Steve and I have been looking into. So here's the parameters. The Kepler co-rotation radius, that is the radius if you take in the rotation of Jupiter and its mass, where would the co-rotation have a velocity equal to the Kepler orbital velocity? Well, it turns out to be 2.3 Jupiter radii. But Io is at 1.5 higher than that. So that tells you any plasma that gets ejected into the magnetosphere of Jupiter gets trapped on the magnetic field and is already rotating faster than orbital velocity. Therefore, it wants to flow outward. It wants to be centrifugally driven outward. And a very similar thing occurs for Enceladus, for the volcano, the eruptive, the ice volcanoes that are occurring on Enceladus. It's a different composition, but so anyway, this is a problem we've been looking at over the last few years, but we haven't published anything. But Steve made this very interesting plot that he got from data from Fran, I guess, Baganel, right? And of the inferred sulfur ion distribution around Io. Here's the Kepler radius. Here is the Io's radius. And this is the concentration of ions, surface density of ions in the Io torus. And you see, of course, it peaks right near the Io's orbit. And there's stuff that's going inward and stuff that's going outward. And however, so this has to be diffusion because things can't go against the centrifugal force. It has to be a diffusion process. There's a high density here, and if there's a certain diffusion coefficient, there'll be some material that goes in. But then most of it, notice that the slope here is steeper than the slope there. So that tells you that there's probably centrifugal, there's centrifugal drift driving material out here. And the question then becomes, if it gets out far enough, does it actually force, does it play a role in the magnetotail reconnection of Jupiter?
Is there an obvious explanation for the steep drop?
Yeah, that's something we haven't really yet. That's in the data. Yeah, we have, and Steve did this, so I have to defer to him. Anyway, this is just meant to be a teaser that possibly we could model this using the drift models. All right, so that's pretty much what I had to say, but I'll give a quick summary. The summary is that magnetic field of a hot star wind traps the material, the wind material, in a magnetosphere. You get centrifugally supported versus dynamically suspended cases. How do the centrifugally supported, the centrifugal magnetospheres empty? Is it by breakout or a leakage? The onset of H alpha suggests strongly, at least for the stars that are most luminous enough, that it's controlled by a breakout. But the very cool stars that have very low mass loss and very low luminosity, may actually be controlled by leakage. But the other thing is that this incoherent radio scales with centrifugal breakout. That is to say, you need rapid rotation as well as strongly magnetic confinement to get radio. And that could be coming from this energy associated with centrifugal breakout. And then there's this potential overlap with both ultra-cool dwarfs and planetary magnetospheres. And so I think the clear implication here is that a burning problem will be to try to model the acceleration of electrons from a breakout event that's induced by a reconnection event that's induced by centrifugal breakout. So what I would like to say is that reconnection is a very general phenomenology throughout all of astrophysics and solar physics. Solar flares or reconnection events. But many of these reconnection events, in the case of the sun, for example, it's very hard to model because they involve some very complex turbulent processes. And so, it's very hard to predict. But in some sense, centrifugal breakout is a driven reconnection, in which you're forcing reconnection to occur. And so, it's going to occur because you're forcing it to occur. So you have a kind of a nice scenario. If you want to do your simulation codes, it's really kind of ideal because it forces it to happen. And now you can just follow the particle accelerations in the reconnection event, see what kind of energies you can achieve. So I've been encouraging people who are reconnection acceleration experts who use PIC codes. And I found out today that Greg is one of these people to look at this problem, because you have a very good, you have a lot of observational constraints that you have to fulfill. One is that you have to make these electrons pretty relativistic in order to explain the radio that you see. And so to me, it's a perfect example of kind of the cross-fertilization of science, where you have ideas from many different fields. And there's potential that there's a connection between stars and massive stars and cool dwarfs and planets and stuff like that. So one of the things we're trying to do is get people who are interested in magnetospheres in general and talk about the commonalities and differences between them. Thank you.
Thank you.